Hello, everyone, and welcome to Intro to Rust Lang Recorded Edition. My name is Connor, and I was one of the original creators of this iteration of the course. In the past 3 semesters of this course's existence, we never officially recorded any of the lectures, so I thought that I would go through all of the lectures and record each of them so that people who are taking the course can view them after the fact, or even if people not at Carnegie Mellon would like to view them, they could have this resource to learn the Rust language. So with that being said, let's get started. So welcome to anyone watching. First, we have to introduce Ferris. So meet Ferris. Ferris is Rust's mascot. Yes, Rust, the programming language Rust, has a mascot, and Ferris will be our mascot for the rest of the semester. So, the very first question that we should be asking ourselves is, why Rust? So, what do we mean by why Rust? So, there's a couple questions here, right? So, like, why Rust as in, why are we teaching an entire course about this, right? Like, why do we have to dedicate an entire course when most programming languages you can just sort of learn on the side, right? So we'll be going over a couple things in the first 15 minutes or so of the lecture. So first question is, what is Rust? How does Rust compare to other programming languages? What are the biggest advantages of Rust? What are some of the issues that Rust has? Finally, who is Rust for? So hopefully I can answer at a high level these questions in the first part of this lecture. So, what is Rust at a high level? So Rust started as a personal project of Graydon Hoare, a Mozilla research employee in 2006. Mozilla then sponsored the project 3 years later in 2009, and then released the source code or open sourced the code in 2010. The first stable release, we can say Rust 1.0, was announced in May 2015. So this is just a bit over 10 years ago. From the official Rust website, Rust is 3 things: fast, reliable, and productive. And we'll get into why they say this and why it really is true and important to say that Rust is these things. So okay, let's zoom in a bit. So what is Rust at a more technical level? Rust is a compiled language, so similar to C or C++, where we compile it to machine code. Technically, that's not entirely true. We compile it to LLVM, and then that compiles to machine code, but that's besides the point. Rust does not have a runtime, so if you're familiar with languages like Python or Java, those have an associated runtime, which also have a garbage collector for their memory management. Rust is imperative, so again, like C and C++, but it has functional features. If you're at CMU, if you're at Carnegie Mellon, and you have taken 15150, you know exactly what this means. We also have strong static typing. Every single thing in Rust is statically typed. Asterisk, that is not always true, but for the most part, Rust has strong static typing. So okay, let's go through a comparison of some of the languages that you're probably familiar with. Most of you watching, if you're at Carnegie Mellon, almost certainly know Python. So Rust versus Python. Rust is significantly faster than Python, on the order of 100 times faster. It is the same order of magnitude faster that C and C++ is over Python. Rust has a much lower memory use, more arguably because Python has a high memory use, but that's besides the point. Rust has a comprehensive type system, whereas Python has essentially no type system. Some might argue that it does. I think people at Carnegie Mellon would strongly argue that Python definitely does not have a comprehensive type system. Go take 15.3.12 for that. Rust has explicit error handling. If you've ever worked with Python and Python exceptions, this is a very nice thing to not have exceptions. We don't like exceptions. All right, Rust versus Java. If you've taken the AP Computer Science in high school, you know Java. I personally have never used Java, but I do know a couple things. Java has a runtime, so the JVM, or the Java Virtual Machine, which also has a garbage collector. It's very similar to Python. In a similar sense, Java has very high memory use, or relative to Rust, it has a higher memory use. We have this thing in Rust called zero-cost abstractions. So we'll talk about more in the future what this means, but in a sense is that every single thing that you do in Rust is explicit. And so things that you like express in Rust do not have underlying or hidden costs. Whereas in Java, from my understanding, you have a lot of things where if you express something in a certain way, there could be a very large amount of stuff going on behind the scenes that could become very expensive and costly with respect to time. In Rust, we have first-class support for modern paradigms as well. So things like enums, or like what we call abstract data types. If you're familiar with the functional languages, you'll know what I'm talking about. Okay, so here's the big one. Rust versus C and C++. If one of the prerequisites of the Rust StuCo is that you have taken 15122 or have equivalent experience with C. So all of you watching should know C. But hopefully the next 4 things that I say will resonate with you. No seg faults, no null pointers, no buffer overflows, no data races. In Rust, we do not have these things by default. If you're like me and learned C during 15122, I ran into countless seg faults and just had no idea how to deal with them until much later. In Rust, we do not have these. Memory safety is guaranteed through the type checker and the borrow checker. Again, we'll talk about what these things are over the semester, but you can be rest assured that you're never going to run into a seg fault unless you really, really try. Again, a lot of the things with Rust is that yes, but asterisks. So just remember that for the rest of the semester. So again, a robust type system with functional patterns. C and C++, while they do have a type system, if you can convert from one thing to another thing with no checks, then that is not a robust type system. Another thing, in Rust we have a unified build system and dependency management. If you ever worked with C and C++ makefiles or C makefiles, personally I think it's a disaster compared to Rust and its dependency manager Cargo. We'll talk about that very, very soon. So Rust is memory safe. So here's a quote. You can pause and think about who said this. I'll just read it out. C makes it easy to shoot yourself in the foot. C++ makes it harder, but when you do, it blows your whole leg off. If you know who said this, that's great. I'll tell you now. It's Bjarne Stroustrup, the creator of C++. So the creator of C++ is saying, in his own language, you can blow your foot off. So what if you had a language that didn't even allow you to blow your foot off unless you really, really, really tried? In Rust, we have safety by default. So everything, unless you have a very specific keyword in your code that makes everything unsafe. Actually, so the keyword is unsafe. Unless you turn that on, it is provably impossible for you to have memory safety violations. So your code is provably memory safe unless you turn on a very specific thing, and that's very hard to do unintentionally. All memory accesses are checked at compile time, which is super great, which means every single thing we do is memory safe. And again, the powerful type system, we'll keep coming back to the type system. It supports memory safety and also thread safety, which are arguably tied closely to each other. So Rust is low level as well. So we've been saying all these great things that Rust has, but at the same time, it gives you these opportunities to go into that deeper level that we're familiar with the languages like C and C++. So again, Rust compiles to machine code, so it's not up interpreted land like Java. Sorry, like Python. It's not interpreted. I think it's JIT compiled for Java. It's not that. Everything compiles down to the lowest level. Again, no runtime, unlike Java and Python. And we can allocate memory deliberately. It'll look a little bit different than C and C++, but you are doing memory allocations. We have support for raw pointers. We have support for inline assembly. Again, like all of these things Rust gives us the power to do. It may not look exactly the same as how you do it in C and C++, where you can just do it wherever you want. Finally, we have zero overhead FFI. So if FFI stands for foreign function interface. As long as a language is compatible with the C ABI, or application binary interface, we're able to interop with those languages. So Rust is also modern. Rust is only 9 years old. Well, okay, technically that's wrong. I'm realizing now that it's technically 10 years old, but I'll fix that in post. Rust is pretty young. Even the 10 years might sound like a lot, but if you compare it to C and C++, which is 50 and 40 years old, it's very young. So because it's young, it has all these really nice modern features. So we have algebraic and generic data types. So I would call generic data types a more reasonable templating if you're familiar with C++. I will say that C++'s templates are more powerful right now, but they're also very difficult to use. We also have modern developer tooling, so things like IDEs and language server support and build management, dependency management, all those things. Like, we get all of these that are built in for free essentially as soon as we bring Rust into our system. Again, yeah, build the system and dependency management. Asynchronous execution is a first-class language feature in Rust. So what do we mean by that? If you've ever worked with async await in JavaScript, that's a whole black hole of discussion to have there, but it's not super pretty. In Rust, it's hard, but it's explicit and quite good, honestly. In Rust, we also have macros and metaprogramming support. Again, like sort of similar to generics and templating, we do have the ability to metaprogram. We're not going to cover it in this in this course, but there's a whole another world of programming and metaprogramming that is very, very cool. So I've said a lot of great things about Rust. However, I need to mention that Rust is not perfect. Rust is far from perfect. Rust is great. Again, this is why we created this course, because we do think it's great, but we have to also acknowledge that it is not a perfect language. One of the issues is that it is a very, very steep learning curve. Rust is very different. It feels very different than to writing other languages. So again, most of you are going to know C and are be familiar with C and Python. When you write Rust, the patterns and designs of how you structure your code are going to feel different. And that is something that there's active researchers trying to figure out how to improve the education of Rust. And there's a whole class of problems that are very difficult to learn, but that's why we're here. That's why we have this course, because it is a hard language to learn. The borrow checker, again, we'll talk about what that is. Like, it will feel like Rust is sort of getting in your way. You'll want to do something, and then the Rust compiler will tell you, no, you can't do that. And very early on, it will feel like it's getting in the way, but later on, you'll realize, no, it's actually helping you. No object-oriented programming, so almost all of you will know what object-oriented programming is, and probably a lot of you will have only exclusively programmed with objects. There is no objects, or in the like Python and Java sense, there are no objects in Rust. So learning to code with Rust can feel very, very different. That's what we're here for, right? Like that's the whole point of this course. Like, this is a hard language to learn. Another issue is the ecosystem. Again, Rust is only 9-10 years old. The amount of adoption is still nowhere near the adoption that C and C++ have, right? Because those are such old languages. There are companies and people who have built so much software in them that the ecosystem is not as large. However, adoption is very quick. People, when I say people, I mean like big companies and small companies, like all companies all across a very wide range of funding, number of people, etc. Adoption is rapid. People are taking Rust seriously, and people are using them to make money, to also build things, to create open source projects. That's a very big thing. Is Rust. A lot of new open source projects are written in Rust, and there's a reason for that. There's other issues. Compile time is quite slow. Compile time in Rust has gotten better over the past 3 years, but it is still very slow. It's on the order of how slow C++ with lots of templating is. On a similar note, it's like interoping with C++ libraries usually requires very complicated bindings. We're not going to talk about this in this semester, but just know that it's quite hard right now, but there are a lot of very smart people are working to improve it. And this is maybe you may not think this is an issue, but programming in a systems language like Rust is still harder than writing in Python. There's no way around it. Writing Python, usually you want to be able to write things really quickly, like ML and AI and scripting. That's what Python is really, really good at. In Rust, it is not as good, simply because it tries to be more correct, and that takes more time. So who's Rust for? So Rust targets really complex programs while providing a stability and security that is sort of necessary of these lower level things. And again, Rust is intended to be fast, reliable, and productive. So recently there was a talk that I was inspired by, and I decided to put this in. Rust is a language for building foundational software. So what is foundational software? This was said by Nico Matsakis, who is the co-lead of the Rust language design team and is also a senior principal engineer at AWS. So what is foundational software? It's not exactly system software. I would say that system software is sort of a more general term. Again, if you're not aware, at Carnegie Mellon, we do have a systems concentration in the School of Computer Science. Systems, foundational software systems is software that other systems rely on. Or put another way, software that other systems are built on top of. And for foundational software, this has a couple, let's say, consequences or requirements for what it needs to be. So foundational software needs to be reliable and secure. It absolutely cannot fail. So when we say foundational software, think about software that sort of lies at the bottom of the tech stack. Things down there cannot fail. So I'm for sure we're all familiar with what happened last year with CrowdStrike. When things at the bottom fail, people lose money, people lose time, people can lose their lives. I'm being very serious. Foundational software has to be that foundation. It has to be rock solid. It cannot fail. Foundational software also has to be performant. What we mean by that is if you have software at the bottom and it's slow, then everything above it is also slow. So you have to have both reliability, security, and performance. And it gets worse. We also need to have stability. We need to have stability in that we cannot be able to make changes to our software and have everything on top of us break because we made a change where the APIs are no longer compatible. We cannot be unstable. But at the same time, we also cannot be stagnant. We cannot take 3 years to add a new feature, because then nothing's improving, right? So we have to be stable, but we also cannot be stagnant, which is quite a difficult problem, but Rust does solve this. So Rust solves all of these problems. It solves problems, there's an argument that it can be better, but I would say arguably Rust so far is the best programming language to do all of these things well. So going back to why Rust. Rust is an exceptional tool with many great features. Again, this is why we wanted to create this course, because we were passionate about it and we really wanted to help people with this. However, Rust is not a magic silver bullet. Please remember this. Rust is not a solution to everything. Rust is really, really good at some things, but Rust is never going to be, and it's not intended to be, the solution for everyone. So in this course, we're going to be teaching you both the strengths and the weaknesses of the language. And hopefully by the end of the semester, you'll be able to explain to someone else who doesn't know maybe as much as Rust as you will, what these trade-offs are. So more specifically, what are the course goals? By the end of the semester, we want you all to be able to read, write, and reason about Rust code. We want you to become an intermediate to advanced Rust developer and be confident, generally confident that you can use Rust going forward. When we say use Rust, we mean go work at a company and write Rust code for them, or like work on an open source Rust project, things like that. Okay, so now we're going to be talking about Cargo, which is, again, Rust's build/dependency management tool. All right, so let's continue with Cargo basics. So to create an executable or something that we need to run, we need a main function. So we define a main function with fn main, as seen right here. And if we want to print something like print hello world, we use this thing, print line with a bang. This is a macro. Don't worry too much about what that is. Just know that this is how you print stuff in Rust. This is different from normal code. We call print line with a bang and write the string hello world. And to compile it, we can use rustc, which is the Rust compiler, rustc main.rs. However, usually, in fact, most of the time, you're never going to actually call or write rustc something, right? We use a tool called Cargo, which is the built-in build system and package manager. So the build system part of Cargo is we build and we can run in a single command. And the package manager manages the dependencies that our code takes on. So if you're familiar with pip for Python or npm for Node.js, this is that. So all sort of bundled together with the build system. So to create a new Cargo project, instead of just a single file, we can use Cargo new. So in this case, we're running Cargo new, and the project is called Hello Cargo. We'll cd into that project, which is just a directory. So inside this Hello Cargo project, or whatever you name the project, you'll find a couple things. So there's a Git repository and a Git ignore. Don't worry about that for now. There's a cargo.toml, which is a configuration file. Okay, we'll talk about this later when we talk more about how Cargo works. And then we have a source directory with a main file in it, main.rs. All Rust files end with .rs. So to build our project, so after we've created it, we can use Cargo build. So we run Cargo build. This is similar to how we compile things in like C. So we do like a GCC do this. Instead, we can just write Cargo build and it will do it for us. This will create an executable file at target. Again, this is a folder under the project directory. Target debug hello cargo, and this is something you can run. So if we want to run this executable, we could do ./target/debug/hello cargo, but that's a lot of type, right? We don't want to do that. So instead, we can run cargo run. So if we type cargo run here, what this will do is it will both build and run your code. So this is a nice simplification. So something quickly to note is that if you have built it in already and you have not made any changes to your code, this compiling step will be skipped. So to check your code for syntax and type errors, you can use cargo check. So this is slightly different from cargo build in that this will run the type checker and the borrow checker and all the sort of things at a high level that are needed in order to compile. So this is the main distinction here is that we don't actually compile when we run cargo check, which is actually very, very nice because in other languages, you usually have to build the entire thing and then sometimes at the very end of that compilation, you find the error. Here, when you use cargo check, you don't have to build anything. It'll just do all the checks for you and tell you, hey, will this compile? And if it doesn't, what the errors are. So it's very useful, especially if you're making a lot of changes. So as a quick recap, we can create a new project with cargo new. We can build that project with cargo build. We can run the project and build and then also run in one step using cargo run. We can check for errors with cargo check, and our executables and also a lot of the things that make things run is in the target/debug directory. Note that if you can, there's also a target release directory if you compile with the release flag. That will make things really fast, but it will also exclude a bunch of debug symbols. We'll talk about that later. Okay, so that's how you build stuff. So how do we actually write code? So variables, hopefully you know what a variable is, because those are in other languages. Variable are values bound to a name. This is pretty common. In Rust, we use the let keyword. So let x equals 5 will bound the value 5 to x. And we can print that variable with this syntax here, with the curly braces and a comma. If you put the x inside here, it is also supported, but that's only supported for some things. Again, we'll talk about this later. So in Rust, all variables are immutable by default. In most languages, things are mutable by default, which means changeable. In Rust, things are immutable, which means they cannot change. So we have some code here. We have let x equals 5. We're going to bound the value of 5 to x, and we print it. Then we have this thing where we're going to bind 6 to x. Notice here on the right, this is Ferris again. Ferris is confused. Some might say Ferris is sad. So why is Ferris confused? What happens when we try to compile this? So again, because in Rust, all variables are immutable by default, if you try to mutate or change an immutable variable, then that results in a compiler error. So here we see one of the really great things about Rust, nice error messages, readable error messages. So if we read the entire error message, we see cannot assign twice to immutable variable x. So we see where x is defined, let x equals 5. It tells us the first assignment to x is here. And then down here it says cannot assign twice to an immutable variable. If you can show me a language within that is older than 10 years old that has these error messages this nice, please put it in the comments or tell me or send it to me, because I would love to know, because in my opinion these are the best error messages, and the people who engineered the ability to have these error messages worked really hard to get this, and we all benefit from it. So another thing is in Rust, read the entire error message. Always read the entire error message. Arguably you should be doing that for every language, but for some languages, C++, it becomes very difficult. So we'll also see that there's a help saying consider making this binding mutable. So instead of let x, it's saying maybe we should do let mute x. So let's follow compiler's advice. So to declare a variable as mutable, we use the mute keyword. So let mute x equals 5, and now everything compiles just fine. If we run cargo run, we get the correct output. And now Ferris is happy. So in this course, we'll be Ferris will be helping us by telling us if things do not or do compile. So we also have constants. So like immutable variables, constants are also values bound to a name, but as the name implies, they are constant. They cannot change ever. You cannot have a mutable constant. That doesn't make any sense. Additionally, constants must have an explicit type. So you'll notice in the previous slides that there were no types. Like we said x equal to 5, but what type was 5? Here we say that this type is U32, and we'll go into what that means. Here's another feature. So we have scopes and shadowing. If you're familiar with the functional languages, this should be similar to what you know. You can create nested scopes with functions with these curly braces. So here we're going to break this down. So I've compacted everything. So we begin with x bound to 5. And then when we call let x equal x plus 1, this is a new variable x. So this is a completely new variable here. Because we're evaluating right to left, because we're evaluating everything on the right-hand side of the equals, this x over here is still bound to 5. So this new variable x is created and bound to 6 here because 5 plus 1 is 6. So then we create a new inner scope by opening with an open curly brace. And now this is a new scope. So this third let statement is going to shadow this second let x. So when we mean that shadow is it's going to, you can think of it as overwrite, but that's not entirely true because we'll be able to get it back after the scope ends. So shadows as in it's covering and the inner scope cannot see the top x. So the shadowed x here is set to x times 2, which is 12. And then we print the value of x here. So this should print 12 here. And the inner scope ends. And then x returns to being 6 again because it's no longer shadowed by this inner scope. Hopefully that makes sense. Make sure to pause here just if you didn't fully understand everything. So if we run this, we see that we get inside the inner scope x is 12, and in the outer scope x is back to 6. So you might be wondering, what is the difference between shadowing and mutability then? Because it seems like we just did the same thing but with extra steps, right? So with mutability, we are not able to change types. So here we have this let mute spaces be a bunch of, like this is what we'll call a stir or a slice. You can think of it as a string. And then we're going to try and assign that string to spaces.len, which is going to, well, I'll say is spaces.len is going to return a usize or a number. So we're trying to set spaces, which was a string, to a number. And Rust is not happy with that. Ferris is confused. What's going on? We're not allowed to reassign a variable to a different type. However, with shadowing and rebinding a variable, we can technically have a different type. The issue here is that when we call let spaces, sorry, not the issue. The thing that's interesting here is that when we call let spaces equals string, this let space is going to shadow it for everyone because it's in the same scope. So after let spaces equals spaces.len, nothing under this code, nothing later will be able to see this original spaces. So a common question that we get every single semester is, who in their right mind would want to do this, right? If you're coming from Python, you're right. If you're in your right mind, you should not be doing this, right? Because variables generally should be one thing. But in Rust, because we have strong typing, this is actually considered like not bad style because we know exactly what it means, and also we cannot shoot ourselves in the foot because this let spaces in the beginning doesn't, like, you can think of it as it doesn't exist anymore. And additionally, because spaces is strongly typed to be a number, we can't misuse it to be a string in any way, unlike Python. So yeah, even though the types are different, let keyword allows us to redefine the spaces variable, which is the difference between shadowing and mutability. So let's keep going. Mutability lets us change the value, and if we will get a compile time error if we try to modify a non-mutable variable. And shadowing lets us reassign, reset what that variable means. And in addition to changing the value, we can also change the types. But when we change the value, the previous one no longer exists. Okay, so we said a bunch of things about types. So what are types? So like most languages, we have two main categories of data types. So we have the scalar types, which are integers, floating point numbers, which is like numbers with a bunch of stuff at the end, Boolean and character. And we also have compound types, which are tuples and arrays. So Rust has similar integer types that you would expect to see in C, although they have a slightly different name. Rust has 8-bit integers that are called IA or UA for signed and unsigned. Signed being it can go negative, whereas unsigned can only be positive. These behave as you would expect. These are 2's complement signed. Everything is pretty standard. The architecture size is the same as size type in C. These are dependent on the architecture. So on a 32-bit machine, these are 32-bit. On a 64-bit machine, it's a 64-bit number. You can think of it as the size of the pointer. Rust also has floating points, so both a 32-bit and a 64-bit floating type. The default one is F64. Oh, I should mention that the default integer type is I32 right here. Default for floats is F64. This is, I believe, similar to what Python does. We have numeric operations, pretty standard. If you're interested, you can pause it here and take a look. Integer casting. So, unlike in C, we do not have any implicit coercion. So we cannot do parentheses, cast to that, and then move on with our data. However, we can explicitly convert using the as keyword. And notably, this as keyword, we are only allowed to cast between very specific types, and it's a lot more strict than C and C++. We have booleans in Rust. We have true or false. As in most languages, if you can tell me of a language where a boolean has more than true or false, or none or null, that doesn't count, then please put that in the comments. That'd be very interesting. Booleans are always 1 byte in size. So Rust has a UTF-32 character type char, or car, or I don't know, however you want to pronounce it. So when we say UTF-32, it means that it can support a lot more than our typical ASCII values. So it certainly does support ASCII values, but also can support these UTF-32 character types. So this is Zeta, and then also some emojis. We can support emojis because we have UTF-32. So what does that mean? What does UTF-32 actually mean? It means 32 bits. So it's going to be much larger than your typical char from C. So char in Rust is actually 4 bytes. And we'll talk about, you might be wondering, like, what in the world? Well, how can char be 4 bytes? Wouldn't that make strings super long? No, because strings use UTF-8, and we'll talk about that in week 4. So char uses single quotes versus strings that use double quotes. Yeah, week 4. Stay tuned. Due to char being UTF-32, char is always 4 bytes. And again, talk more about this later. A tuple, again, if you're familiar with the functional languages, this again should be familiar. Tuple is a way to group together number of values with a variety of types. So you can think of these as, if you're coming from C, structs without field names. We'll get into what exactly that means, but basically it's just a way of packing together data without having to name each of the fields. Technically here, the fields are named 0, 1, and 2, like .0, .1, .2. We'll talk about that later. You can destructure the tuples as so, like we'll call pattern match on. Yeah, we'll talk about this more later. And we can also access the specific elements with .0, .1, and .2. All right, so moving on to the more compound types. Tuple, yes, is a compound type, but usually when we're talking about compound types, we also want to have a lot of data. You would not have tuples with 20 values, right? That's like having a struct with 20 values. So if we want to have a lot of data, we use arrays. So here we have an array of strings. Unlike tuples, all elements must be the same type. So tuples, we were allowed to group together whatever data we wanted. Here we have to have all the same type. Number of elements is always fixed at compile time. So here, let a equals this. There are 5 values in here. So at compile time, we need to know that there are 5 values. Similarly for months, there's 12 here. And we need to know that there are exactly 12 values. So if you're thinking of something that can change size, those are not called arrays in Rust. Those are called vectors. And again, talk about that in week 4. If you want a collection that grows and shrinks, use a vector. So these arrays are basically the same as stack allocated arrays in C. All right, so how do we define an array? So you define an array's type by either filling it in and letting the compiler interpret or like figure out on their own. So again, like I said, the I32 is the default integer type. So if we didn't type anything, it will be able to figure out what the type is, but we can strongly type it if we want. We can also initialize the array such that every element has the same value by putting the default value here and then the length. To access an array element, we use square brackets. This is pretty typical. We use square brackets to index into it. Here we get first and second. And this will, again, 0 index because we're not cavemen. So we have a of 0 is 1 and a of 1 is 2 here. So Rust will ensure that the index is within bounds at runtime. So it will do a check to ensure that 0, 1 are within 5 of, are within the 5 bound. Again, in specific cases, the compiler can optimize that away, but we're not going to talk about that. This is not compilers. No, that's not done in C++ and C, because in those languages, you can do whatever you want, right? And that's why we have buffer overflows. All right, so moving on to functions, statements, and expressions. So like most programming languages, we have functions or routines or procedures, right? We have functions because we want to be able to call other things without having to write everything out like every single time. So this behaves as you expect it would. We call print line of hello world, and we call another function which calls another print line. So all parameters / arguments to functions must be given an explicit type. You can think of it as the only way that we don't have to give specific types is if the compiler can figure it out because there's a default value somewhere. That is essentially asterisk the only time that you can not annotate the type. So in the remaining cases, you're almost always going to be annotating type. So here we have print labeled management. We're going to take a value, which is an integer, i32, and a unit label, which is a char. When we run this, so we get measurement is 5 hours. So because we have functions, we can also return from functions, and we use a typical return keyword. So here we have this +1 function that returns x plus 1. So we go from an i32, add 1 to that i32, and we get a new i32. We can also omit the return keyword. What's going on here? What's going on? Like, how can we return without the return keyword? So if you're familiar, again, with the functional languages, we have this concept called expressions, where a function is an expression and it's going to return some expression. And so here, we're allowed to return the last expression. So we also have this thing called statements, which is denoted with usually with a semicolon. So all functions are a series of statements, which is, again, expression with semicolons, optionally ending in an expression. So here we have let x equals 6, and that's a statement that binds the expression 6 to x, and etc. You can take time to read through this. Statements are instructions that do some action and don't return a value. Expressions, on the other hand, evaluate / return to resultant value. So statements are made of expressions, and a function, again, is a bunch of statements that then returns a final expression. And if you're interested, go to the link, probably in the description and also on the website, and you can find the slides and click on this. So statements do not return a value. You cannot write x equals y equals 6. So y equals 6 does not return a value. This is just will not compile. Expressions, 2 plus 2 is expression. Calling a function is expression. Scope is also an expression. Oh, what do we mean by that? A scope is an expression? We'll talk about that soon. If you add a semicolon to an expression, it returns into a statement. So if a scope is an expression, can scopes return values? So okay, observe the following code where scope returns a value. So we have let y equals opening curly braces, which denotes the beginning of the scope. We're going to call let x equals 3, and then we're going to end with an expression x plus 1. And what y is going to be bound to is the last expression. So in this case, it will be y will be bound to 4. So this is a nice thing. You may be wondering, why would we ever need this? It sometimes makes code cleaner in certain cases, and yeah, it generally follows the pattern of functional patterns. Again, the only reason this works is because there's no semicolon after the x plus 1. If there was a semicolon, then that would be a statement, and then this would not compile. Scopes, again, return the value of their last expression always. So since functions are scopes, that's how they return values. The return, you only need to use return and are actually encouraged to not use return in other cases. You only need to use return if you need to return early. Like for example, if you have a if statement and then you want to return out of the function early, that's when you use it. So let's going back to this code snippet. Functions have to have a specific return value. So again, the functions need to have typed parameters, but it also needs to have a typed return value. If we're allowed to omit this arrow and return type, and that is the same as returning the units type. So in C and C++, this is the same as void, which is incorrectly named. Like it should be unit, because the void type is completely different, which is the never type. But anyway, maybe we'll talk about that later in the semester. But yeah, notice there's no semicolon after the x+1. If we add the semicolon, then it wouldn't compile. Control flow. Let's keep going. So Rust is a Turing-complete language. If you were wondering and wasn't if you weren't convinced yet, this is a Turing-complete language. We define runtime control with if. So here we have let number equals 3. If the number is less than 5, we do something, else we do something else. This is pretty standard. If expressions must condition on a Boolean expression. So unlike other languages where there's truthy and falsy values, we don't have that. You can only have Booleans in if statements, which is, I would argue, is a very good thing. Again, Ferris is confused and sad and doesn't like what he sees. Or it sees. Sorry. So okay, we also have else if branching. You can handle multiple conditions with else if. So again, if this condition, else if another condition. Again, all of these have to be Booleans, not allowed to have truthy or falsy. So if expressions are expressions, so we just talked about how expressions return things. We can have if expressions be bound to variables. So let number is equal to if condition 5, else 6. This is similar to the ternary operator, but more explicit. If expressions must always return the same type in all branches. So this is the reason why it can be bound, because in both or in all of the branches, you always get the same type. So there's no weird stuff happening. All right, loops. There are 3 kinds of loops. We have loop, while, and for. You can probably guess what each of these do. So loop, you can think of as a while true. It will just keep looping until you stop it with break or return, until you stop it with a break or return. So loop will loop forever. So here we have a counter, and we'll increase the counter until it hits 10. So note that break and continue apply to the innermost loop. So the innermost loop being the one that's closest to it. You can imagine if there's multiple loops, then it will only go to the most recent one. Like everything else, you can return a value from loop. So loop is also an expression. Here we have result is bound to what a loop is, and then once the counter hits 10, we're going to break with counter times 2. So this will bind 20 to result. Here's a fun thing that not everyone uses. I've used only a couple times. You can label loops. So instead of having a bunch of go-tos or being weird with your control flow, you can just specify which loop you want to break into, and it will do it for you, which is nice. Again, the case where you want to use this is pretty rare, but it does come up. Here, you can take time to code trace through this and pause. So this also applies to while and for loops. You're allowed to do that as well. Okay, while loops. So while loop, similar to other languages, we're going to continue looping until an expression turns true. So here we have number 3, and while the number is not 0, we're going to keep subtracting. And you can code trace to see what happens here. We also have for loops. So we have a for, we can loop through collections, or here we're looping through an array with a for loop. So this is what we call a for each loop. We can also loop over ranges. So if we want to loop over range, we use the dot syntax to create a range. So this is actually a specified type. For now, we'll just talk about 1 to 4 as just, we can iterate to 1, 2, 3. Note that it is inclusive on the beginning and exclusive at the end, just as all things should be. So as a recap, we have variables and mutability. Again, mutability is turned off by default. We do not want things changing when we don't expect. We have scalar and compound data types, function statements and expressions, control flow, all this stuff, pretty standard. This is not the hard part of Rust, right? This is pretty typical of most programming languages, and we have all of those things. Okay, so now we'll talk about course logistics, which is the boring stuff, but important. Okay, so moving on to course logistics. If you are not a CMU student taking the Rust StuCo right now, then you don't have to watch this. Thank you for watching. If you got to the end, that's awesome. I hope you enjoy the lecture and hopefully future lectures. If you are a CMU student who is taking the Rust StuCo right now, you absolutely need to watch this because if you don't, you are at risk at failing. And especially if you're watching this while taking it, it means that you missed a lecture. And so you definitely need to listen to this and watch it. So okay, you can find our course syllabus linked here or on the website. You need to read it, and you also need to read the entire thing. In a lot of courses at CMU, you can probably get away with not reading the syllabus. I know I did, but I strongly recommend that you read our syllabus because there are things in there where if you don't read or don't understand, you will fail. We have had to deal with this in the past. It was not fun for everyone. So we just please ask you that you read the syllabus and make it easier on the instructors and also on yourself because you won't fail. There's a quiz on Gradescope that is hopefully worth 50 or more points, and that will check if you have read everything on the entire syllabus. So that's free points. It's half a homework, and there's 1,000 points, so that's pretty good for free points. Please make sure you understand the bolded parts. Read carefully, please. So, grading. Attendance is mandatory. This is how StuCo runs. This is not a Rust StuCo thing. This is a general CMU StuCo thing. Attendance is mandatory. We have to take attendance every single lecture. We do take attendance at the end of lecture. However, if the instructors see that people are arriving late, then they are totally they're totally allowed to take attendance at the beginning of lecture. And that's not really fun because then if you're late, you don't count, it doesn't count. So just be on time. Here is the fun stuff. You get a maximum of 2 unexcused absences by the StuCo guidelines. If you read this carefully, it means as soon as you get the 3rd unexcused absence, you fail. It is not, there's no if, ands, or buts. You will fail if you get 3 unexcused absences. And this is not a Rust StuCo policy. This is a CMU StuCo general guideline, and we're not allowed to break away from it. So, just to be very clear, again, I'm just going to say it again. This 2 means that if as soon as you hit 3 unexcused absences, it is done. You fail. And we really do not want to have to deal with that. So please show up. However, obviously, you're all busy students, so there are ways to get around this if you tell us beforehand. I'll get into that later. So homework and programming assignments are worth 100 points each. To pass, you need to get everything. You need to finish all the assignments. And that might seem very hard, but it's not as hard as you think because of a couple of reasons. So yeah, 1,000 points to pass the course. So you need to do 10 assignments that are each worth 100. There's a lot of extra credit, a lot of things worth more than 100 points. This is not terrible. Communication. So everything should be done on Piazza. So things about questions of the homework, excusals from lecture, extensions on homework, all of that should be done through Piazza. If you email us, you can email us, but it's it's very likely that the email will get lost and then things don't go well. You can communicate to us via the unofficial Discord. We would strongly prefer to be on Piazza. If you're interested in the Discord, go join it. It's a lot more casual there. And again, email if you have something very serious that you need to only email the instructors and not TAs, then you should email, and yes, or even better, speak to the instructors in person. Talk to us. So talk to us via all of these. If you're struggling with something, or if you don't think you can finish something, or if you can't make it to a lecture, tell us beforehand. As long as you tell us beforehand, we can do something about it, right? If you don't tell us beforehand that you're going to miss a lecture, you're getting that unexcused absence no matter what. There's nothing really we can really do about that. Okay, continue about the homework. So homeworks are designed to take less than an hour per week. This is a 3-unit course. Technically, you shouldn't be spending no more than 1 hour in lecture and 2 hours on homework, but we try to make them less than an hour per week. If you're spending a lot more than that, please let the instructors know. All the assignments are auto-graded through Gradescope. So you can... All the tests are also public. So if it passes on your machine, it will likely pass on Gradescope. If it doesn't, then something has gone strange. So yeah, test locally and then upload to Gradescope and you should be fine. However, you should make sure you check the Gradescope output just in case you are missing some lints/formatting. Okay, there's official 7 late days for anything. If you turn in something late, like a couple days, and you only do it a couple times, you don't even need to tell us. You'll get 7 late days for free. If you need more, then you need to tell us. And we may or may not give them out very easily. Just ask. Just talk to us. Just talk to us. Okay, so here is the fun slide. Homework solutions. We have made all homework solutions public on our GitHub. So all of the solutions are public. They are there. You can look at them. We very, very strongly encourage students to not look at these because, again, this is when you're learning a new language, you want to be building the connections in your brain to think for yourself, right? If you look at these solutions, then you're not really building those connections. This also applies to AI tools that can solve these things for you. If you use them, you're not going to be learning that much from it. Obviously, we cannot tell if you're sometimes we can tell. Sometimes it's very obvious if you copy and paste something, but this is a StuCo. You're the one who decided to take it, so you might as well learn and not spend too much time. Like, if you're using a bunch of AI tools, like the code agents, then really you're wasting your own time. This is a 3-unit course. This doesn't count towards graduation, so we don't know what you're doing. So give a good faith attempt without AI tools and without looking at the solution before resorting to doing those things. And if you do resort to that, just tell us. If you tell us beforehand and you say, like, hey, I needed to do this because I didn't have time because I was working on Malloc, we understand. Just tell us in advance and we can work with you. You will not learn anything from copy and pasting our code. We will also look at all of the code solutions. If we see that you have copied and pasted our solutions, we have to file an academic integrity violation. And again, we don't want to do that. As happened before. Please make it easier on everyone. Yeah. So, okay, homework 1. So homework 1 is just a series of small puzzles. This is going to be very different from a lot of the later homework assignments. It's 8 small puzzles and 4 simple function implementations, which you can go, which are from 15.1.12. You can just look at the 15.1.12 website for the solutions in Python and then convert those over into Rust. So again, the objective here in the early stages is to just build confidence with the syntax and experience interpreting error messages and reading those error messages. We don't want really, this should not be a hard homework. It should be just like go through the motions of getting familiar. Refer to the README and the documentation and the write-up on the website. Please let us know if you have questions. Again, please talk to us. If you don't talk to us, we can't do anything to help you. All right, next lecture is ownership, which is part 1. These are all the past instructors and creators of the course. Okay, thank you for watching. I am planning on recording more of these lectures. I don't know if I'll have time because I'm no longer a student. But yeah, hopefully I will find the time to do so. And let me know your thoughts in the comments and any feedback. So yeah, thank you and have a good day.